we've talked in the previous video about three sort of extreme cases for transmission line terminations. So we had the one case where the transmission line is terminated in an open circuit. Then on the opposite end of the spectrum, we had a transmission line terminated in a closed circuit. And so if you think about it, the one on the left, the open circuit, is just a transmission line being terminated with an impedance of infinity. Because in an open circuit, you have no current, but you have some voltage. And so Z is equal to V over I. If I equals 0, like in an open circuit, then Z would be infinite. And so you're essentially in an open circuit transmission line, you're terminating it with Z equals infinity. In a closed circuit transmission line, or short circuit transmission line, actually I'll call it a short circuit. In a short circuit transmission line, you're terminating it with Z equals 0. The terminating impedance is Z equals 0. Because again, Z equals V over I. In a short circuit, the voltage is 0. You have some current, but the voltage is 0. And so the impedance will be, the impedance is going to be 0 for that short circuit case. Then there's sort of the in-between perfectly matched case where you have a transmission line that is terminated in some impedance. Z equals Z naught. And Z naught is going to be for, I'm just going to draw it out in the rest of these. So Z naught is going to be the characteristic impedance of this transmission line. So like for a given transmission line, it just acts almost like a resistor with the value of Z naught. And so when you terminate it in an actual resistor of a value of Z naught, or just in an actual impedance with the value of Z naught, then the line is matched and you don't have reflections. In these other two cases, in the one where you have the open circuit and the one where you have closed circuit, short circuit at the end, you have reflections. You launch your incident wave. This is the incident wave. It's coming in, and it reaches the end of the transmission line. Reaches the end of the transmission line, and it bounces back. You have a reflected wave. So let's look at the open circuit case on the left here. Let's say you launch the incident wave of positive 1 volt. The reflected wave, in this case, will also be positive 1 volt, because we talked about how in the open circuit case, the polarity and magnitude of the reflected wave are the same as that of the incident wave. So polarity is the same because both of these have the same sign. If the incident wave was negative 1 volt, the reflected wave would also be negative 1 volt. They have the same sign. And the magnitude is the same because they're both 1 volt. If the incident wave was 2 volts, the reflected wave would be 2 volts. Now, in the short-circuited case, let's say you launch 1 volt onto here. What you'll see is the reflected wave will have the opposite polarity, but the same magnitude. So the opposite polarity, because now it's negative, or if it originally was negative, if the incident wave was negative, the reflected wave would be positive. So you invert the polarity, but you keep the magnitude the same. And the magnitude is just, the reflected wave is just the same as the incident wave in magnitude. So you have these two extreme cases, sort of the Z equals 0 case, where you have the reflected wave having the negative polarity, and the Z equals infinity case where Z equals where the reflected wave has the same polarity. And then you have the middle ground. You have the incident wave, and I'll just draw a reflected wave just for symmetry. But if I were to launch like again plus 1 volt onto here, you would see 0 volts reflected. You wouldn't see a reflected wave. So those are sort of the three cases that we have. And by the way, this diagram that I've been drawing, it's referred to as a bounce diagram, and it sort of just shows the incident waves and the reflections. And the way that you can calculate at any point in time what the voltage is on the line at any horizontal position. The horizontal axis here on the bounce diagram represents the position along the transmission line, and the vertical axis represents time. So if I wanted to find out at this location on the transmission line, what is the voltage at this time, and also at this time, you just sort of just draw a line down here, and then okay, now we've intersected the time axis there. So what you do is you add up all of the arrows that you've intersected with this vertical line that you've drawn. So far we've intersected the 1 volt line. So at this location on the transmission line at this time, we're seeing 1 volt. You just keep drawing that down. Intersects here again. Now we've intersected 1 volt and 0 volt. So it's still going to be 1 volt. But if we had done this on the open circuit or short circuit case, we might see at this time we would see on the open circuit case we would see 2 volts because you're adding the 1 volt and the 1 volt. Here, the closed circuit case, you would see at that time you would see 0 volts because you're adding the 1 volt and the negative 1 volt. So that's just how you read a bounce diagram. So this has been sort of a really quick overview of these three sort of types of transmission line terminations, and the next video is going to explore what if you terminate it in something that's not one of these three.